Okay, so here we go for the practice problems for the EC312 final exam. This is covering some of the signals problems that we've had in the last part of the course, and just making sure you have some idea of what might show up on the exam. So, problem one, we see an antenna radiation pattern, and the first question is, what is the beam width? So, a couple things we want to make a note of here. The beam width is always going to be at -3 decibels. So that's what we're sort of looking for on the, and that's the beam width. So we're looking for the at -3 decibel point on this pattern here, and it's asking for the main lobe. The main lobe is at 0 degrees. So whichever thing is pointing at 0, that's the main lobe of the antenna, and that's what we're looking for the beam width of. And so we have to take a note here that the pattern shown is -10, -20, -30. So each of these lines is -10 decibels, which means that we need to find somewhere in between this. Halfway between would be 5. A little less than that would be -3. So maybe around this point is where that main lobe intersects with the circle that is -3 dBs. So if we sort of drew this -3 decibel circle here, that's what we're looking for, and that's the angle at which the beam width is half power, right? -3 decibels corresponds to half power. So then we just draw out from that point to the edge of the circle, and we see that it's sort of -30 and 30. So 30 plus, or 30 minus -30 is going to give us 60 degrees is the beam width. So really, again, all we're doing is just measuring between those 2 points where the main lobe, which is at 0 degrees, intersects with -3 decibels on this antenna pattern. And then we measure between those two lines. So 60 degrees for the first one. On to part B. Imagine that the main lobe of the antenna is pointed at your desired target, which is a mile away. The target receives 10 milliwatts. A sneaky spy has positioned a receiver also a mile away, but behind the transmitter at 180 degrees. What power level would the spy observe? So we're looking at now for part B at 180 degrees. So we're asking how much power do they get there? And so we want to look at this point where the back lobe of the antenna intersects with the rings and just see how many decibels it's getting. So we can see that it's got -10, -20. So -20 dBs is what they're receiving, and that's an attenuation, right? Decibels are generally used for amplification and attenuation, so it's -20 decibels attenuated from the main power level. So that 10 milliwatts that we're sending out the front, if you're at 0 degrees, you're receiving 10 milliwatts, but if you're at the back, you're receiving -20 decibels of that 10 milliwatts. So we've got to figure out what our amplification is, and our amplification for milliwatts is going to be 10, converting decibels to unitless gain. 10 to the -20 over 10. And so it's going to be 10 to the -2 is really what we're getting there. And we're going to multiply that, or that value is going to be 0.01. And we're going to multiply that, power 180 is going to be that 0.01, which is the power attenuation that we're receiving at 180 degrees, times the 10 milliwatts that is being sent out in the first place, and that's going to give us 0.1 milliwatts in total. So that's all we're doing there. Again, it's just understanding that the 180 degrees is receiving -20 decibels, converting that to unitless gain, and then maybe more appropriately, this should be labeled G equals 10 there, because that's what we're calculating is the unitless gain, and then we have the gain times the original power. In this case, it's attenuating, so it gets smaller. Okay, so on to problem 2. This is a Friss free space equation problem. Highly recommend having this, on your note sheet just in case. And I would also highly recommend having the form of it where we have calculated or reworked the equation to have the distance on the left-hand side instead, which is distance is lambda over 4 pi, and then square root of pt gt gr over PR. So that's just, we multiply through by 4 pi d squared. We divide by PR. We divide by 4 pi, and then, or 4 pi squared. And then we take the square root of everything, which the lambda and the 4 pi come out of that. since they were squared inside, so now they're not squared outside, and that gives us the distance. So this is a useful equation to have, just because often we're going to ask a question like this one, which is, how far away can you be, or what is the distance that you're receiving this power level of a signal at, or something like that. So for first free space, we're really just trying to find all of the things that we're going to plug into this problem. So your cell phone transmitted a power level of 500 milliwatts. So our PT, power of the transmitter, is 500 milliwatts. We're going to need to make sure that that's at the same level as our communication, or our received power. So we want to make sure that those two terms are in the same units, so that it makes sense. And so we'll probably write this as 500 times 10 to the negative third watts. So just converting everything to watts or milliwatts or picowatts, as long as they're in the same units, it's fine. But we need to make sure that these are in the same place. We have our receiver is receiving at 10 picowatts. So PR is equal to 10 PW, which is going to be equal to 10 times 10 to the negative 12 watts. So picowatts. And again, this is maybe a useful thing to have on your equation sheet if you don't remember, milliwatts, microwatts, nanowatts, picowatts, etc. Like making sure you have those abbreviations down, and what power of 10 that corresponds to. And likewise, in the other direction, kilo, giga, and tera would be useful potentially. So that's our PR and PT. We need our GR and GT. So GT, the cell phone antenna has a gain of 1.58, so 1.58 is our gain. And then our tower is a gain of 3.16, so GR equals 3.16. Again, important for both of those terms to be either unitless gain, actually really just to have the both in unitless gain. So if we give something in decibels, make sure you use that conversion we used in the last problem to convert that to unitless gain instead. So that's a lot of our parameters. So we have PT, GT, GR, PR. We need lambda, and that's it. So lambda is going to come from the frequency, and we know that lambda is c over f. That's the wavelength, is the speed of light over the frequency. So that's 3 times 10 to the 8th meters per second for this class's purposes, and then 700 times 10 to the 6th, since it is megahertz, and that's going to be hertz. And so then we end up with something like 0.4286 meters is our wavelength for that. And past that, it's just a matter of plugging this into that equation, right? So we've got our 0.4286 over pi times PT, which is 500 times 10 to the negative third watts, times the two gains, which is 1.58 times 3.16, over the received power, which is 10 times 10 to the negative 12 watts. We work that through, and we should end up with 17041 meters is how far we can stray from that equation, or from that tower. So again, this is really just plug and chug. I would have both of these forms on your equation sheet so that you can do it quickly, and really it's just a matter of reading the problem, figuring out what PT, PR, GT, GR, and lambda are, or in the event that you're given distance and asked about the received power, or how much power do you have to transmit, again reworking this original equation so that you have the right term. So that's it for problems 1 and 2.